Welcome back. This is Mr. Greenstein's Geometry. We're in section 4.4, Congruence and Transformations, and we're going to be talking about a theorem first, Reflections and Parallel Lines Theorem. So if we have two parallel lines, we'll say K and M, and we have some figure, we'll just say this segment AB. If we reflect it across K first, and then reflect it across M, then we're going to find something interesting. The effect is, though, if we move from AB all the way to A double prime, B double prime, it's as though we just translated this from start to finish. And what's also interesting is that the distance has something to do with the parallel lines. So the movement for point A to become A double prime, it's going to move perpendicular to the two lines, and the distance from A to A double prime is 2 times the distance between the two lines. So it moves perpendicular, and it also moves a distance that is 2 times the distance between the perpendicular lines. That's the theorem for reflections and parallel lines. So in this diagram, we're taking GH and we're reflecting it across K and getting G prime H prime, and then reflecting it across M to get G double prime H double prime. So name any segments congruent to GH. Well, GH is going to be congruent to G prime H prime and to G double prime H double prime. HB, which is this segment here, is congruent to B H prime, because when we do a reflection, the definition of a reflection is that these two segments have to be congruent. The same thing with GA. GA is going to be congruent to AG prime because of a reflection. The next question is AC. A to C, is that the same distance as B to D? And the answer is yes, because we have parallel lines here, and we have a perpendicular line here. And this has to be a perpendicular line because by the definition of reflection, reflections have to be across a line of reflection perpendicular. So this distance here, BD, has to equal AC. And then what's the length of G to G double prime? Well, we know that HB is 9, and we know that D double or H double prime is 4. Well, this is 4, then this also has to be 4 over here. So that's 4, and then we have, this is 9. So 9 plus 4 is 13, and that makes the distance from here to here 13. Therefore, if we measure from G to G double prime, it's going to be twice that, or 26. That's the length. Reflections and intersecting lines theorem. Well, if we take two intersecting lines, K and M, and then we take a figure like this segment AB, and we reflect it across K, and then reflect it across M, we'll find that the resultant is, though we did a rotation over to here, and the rotation is around this point P, which is the intersection of the two lines. And another thing that we find is that the angle of rotation is going to be 2 times that of the angle between the two intersecting lines. So if this is x for x degrees between these two lines, then it's going to be from A to A double prime, it's going to be 2x rotation around point P. And that's the theorem. So if we look at this in the diagram, we have two intersecting lines, and we reflect across line K, and then we reflect across line M. It's as though we took this figure and just rotated it around until it finally got to this green figure over here. And since the angle between these two lines is 80 degrees, then we know the angle of rotation from here to here is going to be twice that, or 160 degrees. So that's for section 4.4. We're going to continue this conversation in the next day.